So before I actually start, let me point out. Well, let me point out to everybody. You remember? Notice all the emails you've been getting about this workshop. You notice who they're all from. You notice all the snacks there and the video and stuff, and you notice the absence of IT staff and department staff and people like that are usually there arranging all of these things. Alice and Carl are doing the entire thing, and so just. But they're not. Anyway, I just wanted.
They're doing the second half.
I just wanted to point that out. All right, so let me give you a talk about. I guess I should start with some words about NTRU. I'm really kind of excited about this lattice-based thing that I want to talk about. So what I'm going to try to do is lead into that and segue into that in as subtle and quick a way as I possibly can. But let me first mention a couple of words about historical context. This workshop is on lattices with symmetries, and thank goodness people are saying that symmetries are interesting and fun. You have no idea what people thought about lattices with symmetries in 1996. It was not a pretty sight. It was, in fact, well, less said about that, the better. Also, by a tremendously funny coincidence, I started thinking about this stuff in spring of 1994, and I came up with a couple ideas that I'll tell you about. But I realized by spring of 1995 that the question that it all boiled down to solve these crypto systems all boiled down. That was a joke, by the way. All boiled down to doing lattice reduction effectively. In other words, finding the smallest vector in a lattice. And back in the early 90s or middle 90s, people believed that LLL would always work magically in any circumstance. That it was hopeless. The opinion was it was hopeless to build cryptographic systems based on lattices because LLL would just find the answer, and there you are. And I remember. I remember saying that something about this problem just felt exponential to me. It just did not feel polynomial. And I was sure that as the dimension went up, the difficulty of the problem had to grow at least exponentially. And I remember sometime in the spring, Henrik, you probably don't remember this, but maybe you do. I called you up. I arranged to talk to you at Berkeley. I was at MSRI at the time, but I was helping run this program on automorphic forms at MSRI. But you were just down the hill, so I called you up and I met you for coffee and asked you, so how effective, how much does it take to actually find shortest vectors in lattices as the dimension gets high? And I remember your answer was, how the heck do you expect me to know? I'm a theoretical mathematician. So that's what I realized. I had years of computer experiments ahead of me trying to figure this thing out. Anyway, I want to tell you a little bit about how the whole thing began. It all began. I was thinking about polynomials, and I started thinking about something entirely different. But I began thinking about polynomials, and I remembered thinking about polynomials. I wonder how much I could get away without writing. Let me see. I started thinking about. Well, yeah. Actually, I better write. I started by thinking about polynomials of the form f of x is equal to the sum of ai x to the I, where I goes from 0 to n minus 1, and where, for example, where the AIs were chosen from the set 1, 0, and negative 1. And so I started thinking about this, and I realized that that if you take an f of x that looks like this and a g of x that looks like this, bi, bi x to the I, and you consider these f and g as being inside the ring z of x modded out by x to the n minus 1, then if you took the product of these things, f and g, and you just wrote, say, h is equal to f times g, and I'll use the star to indicate that multiplication is going on in this ring, then the coefficients, then if h was equal to the sum of, let's say, cj x to the j as j goes from 0 to n minus 1, then these coefficients cj were of the form the sum over the sum over I1 plus I2 congruent to j mod n of a sub I1 b sub I2. I think that's what it is. And so I was thinking of that as a kind of dot product. Basically you think of the coefficients of f and the coefficients of g as being points on a circle, and take the dot product of two circles to get the first coefficient, then rotate it one slot to get the coefficients of the next component, and rotate it again next. And the thing is that these CJs, if you do that, are going to be roughly less than the square root of n, because they're mostly going to cancel out, and it's going to be very unlikely that they're going to get very big. And so in other words, so I thought of this as short, something like this is short, something like this is short, and then the product is therefore being pretty short. And the first question I was trying to think of was, how the heck can you build a crypto system where the hard problem is given h equals f times g with fg short, find f and g. And the fact that this was the original problem that I was actually thinking about trying to build a crypto system out of is connected to the fact that the crypto system that Craig and Mike so thoroughly broke was sort of built out of problems like that. That was built out of a whole lot of v times a, v times a1, v times a2, v times a3. It's all because I was thinking about this general thing. So that was the question: how to do that, and then a signature scheme. It turned out to be possible to develop a signature scheme out of that called PASS, for Polynomial Authentication Signature Scheme. So I did that, but I'm going to skip that for the moment. But that's what I want to get back to. That's what I would get back to. The earliest thing that ever came out of this turns out to actually have a wonderful, I think, incarnation today. But the hard problem that eventually NTRU ended up getting based on was this: that if we move from R to RQ, if we let R sub Q equal Z mod QZ of X modded out by X to the N minus 1. Then if you pick f at random, oh, and let's call the collection of f's. Let's call the collection of f's that are trinomial, whose coefficients are chosen for either 1, 0, or -1. Let's just call that t of n, just for shorthand. And so, let's see. Well, put it out by x to the n. I know. I'm not calling trinary. I meant trinary. Yeah, right. Yeah, no, definitely n doesn't equal 4 or 3. Anyway, let's see. So if you take something like this, then if you pick a random f inside of t of n, then with high probability, there exists an f also inside of RQ such that f times capital F is congruent to 1 mod q, and also, of course, mod x to the n minus 1, because everything we do is mod x to the n minus 1. So most things are going to turn out to be have inverses. The only time they won't have an inverse is if mod q they have any factors in if f mod q has any factors in common with x to the n minus 1. So for example, you certainly don't want f of 1 to evaluate to 0. But if you pick one at random, if little f is of high degree, and you choose it so that, say, has 2 factors mod q, then the chances of picking one at random that has an inverse is exponentially good. So you're probably going to be fine. So then I realized that there was a very neat fact that happened, which was that if you start with f inside of t and you map yourself to f inverse inside of just general RQ, then this thing looks random. Just the structure of you see, the trinary polynomial is short, and it doesn't usually make sense to consider shortness in a mod q situation. But in fact, it is short, and if q is anything like a couple of hundred even, then a randomly chosen element from RQ will look very different from a randomly chosen element from T. So that looks random, and that meant, in particular, if you choose f and g from T, then f inverse times g looks random. Looks random as something inside of R sub q. And so that, at some point I suddenly realized, well, there's a hard problem there. Anyway, I realized that the useful hard problem to consider was this. Given h inside of R sub q, find a short f such that f times h is also short. So it doesn't have to be trinary or anything like that. Just general hard question was that. Just Damian Stella has, in the last couple of years, shown that actually the H's really are distributed in an extremely pseudo-random way inside of R sub Q. So back then, I just thought, well, they sure look random, kind of like what you were saying, look random. And the dice could have gone the other way. They could have been totally unrandom, and I just didn't realize it. But luckily, they turned out to actually be random. And then the question was how to build a crypto system out of this hard problem. And the answer, well, there must be other answers, but one answer turned out to be, take, for example, consider, say, 3 times, the answer turned out to be define define H congruent to F inverse times G, where F and G are trinary. And then choose M and R at random from T. We'll let M, and M is going to turns out to be the message. So your message is going to be something trinary. Your R is going to be some random thing. When I say M, choosing M random, I just mean because in a primitive this is just the message. But in the actual cryptographic constructions, M has got to be different. Every encryption of M has got to be different, or at least has got to look different, or at least can have no possible association with M. So. And it turned out there was a very simple way to do encryption, and that was let the encryption of M equal 3 times H times R plus M. That was it. So this was R consists of, well, H is random stuff mod Q, well, looks random mod Q. R has just got 1s, 0s, and negative 1s in it, so the process of computing this thing is quite fast. And so encryption goes pretty quickly. And then to decrypt, you just construct first, let F times E is equal to 3 times F times H times R plus F times M, and that is congruent to 3 times G times R plus F times M mod Q and mod x to the n minus 1. So you just, if you take F to be your private key and you multiply the encryption by F, then the F cancels the F inverse inside of H, leaving only the G. So you have 3 times G times R plus F times M. And then the neat thing is that R is short, G is short, 3 isn't too big, M is short, and F is short. And so the product of these things, when reduced mod Q actually equals the real, the genuine 3GR plus MF. In other words, if these were big enough, if the M's and the F's were big enough that some sort of reduction mod Q went on in this kind of thing, then forget it. You wouldn't get these things back. But because they're small, you get these back. And once you get them back, you could reduce mod 3. And if you reduce mod 3, that goes away. You're left with m times f, but you know f, so you know the inverse of f mod 3. And you could multiply by that and recover m. So that turned out to be a kind of an interesting crypto system. But what I really want to talk about is something that predated this. So there was, before this idea came along, there was something else that was going on, and that was the following. It also based on this notion of shortness, but without the F inverse, without making any use of the existence of inverses mod Q. And that goes like this. Suppose you choose Q to be congruent to 1 mod n. Then, if you let, if alpha is a primitive root mod, let's see, if alpha is a primitive root mod Q, and let me write actually, Q is equal to 1 plus k times n. So if alpha is a primitive root mod Q, then alpha alpha to the k, alpha to the 2k, let's see. I think I'm alpha to the nk, alpha to the n minus 1k, nk. I think well, let me just write dot, 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 because I'm not exactly sure where it ends. Alpha k, yeah, I'm very bad at that kind of stuff. Alpha k, alpha 2k, that are all nth roots of 1. No, it doesn't have to be. Oh, sorry. Sorry, I was in NTRU world. Q has to be prime, yes, in order for the group to be cyclic, in order to have the primitive root, right? So you have to choose a pair, and you want n to be prime because of a talk that Craig gave it at Crypto a long time ago, and you want Q equal to 1 plus kn to be prime also. And so you've got these bunch of nth roots. And so what's the good thing about these nth roots? Well, let me abbreviate them. Let me say alpha 1 is equal to alpha to the k. Alpha 2 is equal to alpha to the 2k mod q, or something like that. So just to avoid writing exponents all the time. So these are distinct nth roots. Now, the mapping from R sub q to z mod qz given by f gets sent to f of alpha I is a ring homomorphism. Not only is, by Fermat's little theorem, not only is that evaluation map a homomorphism, but in fact, if you take alpha 1, alpha 2, up to alpha t, where in practice I'll take t to be approximately n over 2. If you look at these, then the mapping f to f of alpha 1, comma, f of alpha 2, comma, dot, 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 up to f of alpha t is also a ring homomorphism. Now going to z mod qz, to the t power. Now, and in fact, it's a very particular type of homomorphism. If you think of, you could think of, on one side, we have functions. On the other side, we have Fourier transforms of the function. So if f, you think of f as the function given by the coefficients, and then the Fourier transform of f is the collection of all evaluations of f at distinct nth roots of 1. So what this is a mapping from a function f to a partial Fourier transform of this. And there's something very, very neat that happens with Fourier transforms, and that's called the uncertainty principle. And that basically says that if you concentrate your function at one point, the Fourier transform is going to be dispersed. And the more you concentrate, the more dispersed the transform is going to be. And so what that means in practice is that f, if we start with f in trinary, that maps to, apparently, that maps to what we just call pseudo-random in z mod qz to the t. Looks very difficult. So we now have a hard problem, and the question is, can we base some sort of crypto system on it? That hard problem is given some vector v inside of z mod qz to the t, find f short such that f maps to v under this Fourier transform map. Now, if you think about it, this hard problem is a lattice problem. This basically, what you're looking, you have a matrix. You have 1, alpha 1 squared, up to alpha 1 to the n minus 1, down to 1 alpha t squared, alpha t to the n minus 1. And you're taking this matrix and you're evaluating it at 1, 0, 0, negative 1, dot, dot, dot. You're evaluating at something chosen from t. In other words, the evaluation of a polynomial at the alphas is the same thing as the product of this matrix times a vector consisting of 1s, 0s, and negative 1s. And so it has so the answer will then be f of alpha 1 down to f of alpha t mod q. And the problem boils down to, you know this matrix, and the problem boils down to trying to find a short vector that solves this equation. That turns out to be very easy to translate into a closest vector problem. But the closest vector problem happens by accident. The reason the problem is here is because of the uncertainty principle. But it's curious that the uncertainty principle question boils down to this closest vector problem. And the reason, and by the way, the reason why it boils down to is if you forget this, if you look at the null space of this linear transformation, then you could easily pick some solution to this, not necessarily short. And if you think of that as a vector, if you were able to find the closest vector in the null space of this linear transformation, and the difference between that closest vector and the point you started with would be your target. Yes?
I think I think you have the answer, but just for clarification. So isn't the FFT invertible?
Sorry?
FFT is invertible.
Oh yeah, FFT is invertible, but this is only half of F. And so the point is you're given half of the Fourier transform information. So probabilistically, F is invertible. The probability of there existing two such F is negligible, but in reality, it's incredibly difficult to recover it. And that's where you have the trade-off. You know, it's tempting to have T be really small, make it virtually hopeless, or it's tempting. But if you make T very small, it turns out that it gets very easy to defeat a cryptosystem based on this kind of thing. Anyway, so it turns out that T about n over 2 is a reasonable choice for this. How to build a cryptosystem out of this? Well, here's how. And I couldn't figure out how to build a cryptosystem out of this, but I was able to figure out how to build a signature scheme out of this. And the way the signature scheme worked was private key F inside of T of n. Public key, well, certainly n is public, certainly q is public, certainly the alphas are public, and the values f of alpha 1 up to f of alpha t mod q. And so the hard problem now points down to I claim I have a short polynomial that takes these values. How do I prove that I know this short polynomial without revealing the short polynomial? So you want to do this. This is your objective for a signature scheme. So here's what you can do. I'm going to explain this in terms of commitment and challenge, but it's the same thing as doing a digital signature. So commitment. Does everybody have the same trouble as I do remembering how many T's there are in commitment? So the commitment is you choose a secret G in the trinaries, just like your private key, and your commitment is you reveal a collection of values, alpha 1, of G of alpha 1, G of alpha t. And challenge C. Also kind of small, trinary. Okay, so you reveal your commitment, you receive a random challenge C, which you hopefully weren't able to expect. In reality, C of course will be a hash, an output of a hash function that involves your private key, that involves your public key and your commitment and the document you're signing. And challenges that, and output signature is F times, well, the signature G times F plus C. That's not really what I want as the final answer yet. That turns out to be the wrong linear function. But output, you could basically think of this is any polynomial in G, F, and C with small coefficients. Yeah?
Sure shouldn't be CF plus G instead?
I am quite positive that it should be CF plus G because of reading your paper. And that's what I was coming to, because the whole reason why this thing suddenly got revived was I was about to come to some recent work of Vadim. But not knowing about that, because this was maybe 17 years before that or so, I don't know. I said this, and verification is 2 steps. G times F plus C is small, and 2, G of alpha I times F of alpha I plus C of I. Oh, let me call this H. And 2, H of alpha I is equal to G of alpha I times F of alpha I plus C of alpha I for every I. So in other words, the proof is in that, first of all, this is small. This is small because it's products of things that are small. And secondly, it satisfies this because the evaluation map is a ring homomorphism. The hard problem that a forger would have to face is exactly the same as the original problem, finding a short polynomial with specified values. So what's wrong with this scheme? And I started working on this with well, basically I bounced ideas off Bert Kaliski for an entire year of 94, 95, which was a lot of fun. And Bert Kaliski pointed out, after a year, pointed out a fatal flaw that a system such like this has. And that is transcript leakage, very serious transcript leakage. And the way such a thing like that works is, well, there are several options. An attacker has a few options. The most basic option is consider average H times H reversal for a long list of H. Remember Craig was talking about this process of averaging things times the reversal? Well, what happens in this particular case, if you do that, is you end up with G times F plus C times G reversal times F reversal plus C reversal. And this is equal to G times G reversal times, now what are you going to get? You're going to get F times F reversal plus F times C reversal plus F reversal times C. I'm leaving out this well. F reversal times C plus C times C reversal. And suppose you average a whole bunch of these things. Well, assuming that the G's are chosen to be uniformly distributed and small, this is going to head towards a known constant. This is going to head towards 0 this is going to head towards 0, and this is going to head towards known constant. So the output of this thing was that this eventually yields the value that Craig was talking about, oddly enough, the Gram matrix associated to F. And we viewed that as a disaster anyway. This was a couple years before Craig found the way of solving that problem. But we assumed that the Gram matrix problem wasn't sufficiently hard to base a crypto system on, and so that's one of the reasons why we just figured this plane didn't work. There was an even better reason to assume it doesn't work, though, because what you could actually do is you can let's see. Well, never mind. I won't go into the other. There's even simpler averaging techniques, which will just get you F directly, without even bothering to go through the problem of factoring the Gram matrix. Okay. And so this was bad. This was bad. I tried to patch it up in God knows how many ways. You know, more complicated linear functional stuff like that. It was basically doomed. Okay, and the reason was it was subject to this averaging attack. Well, that's where the matter stood. A couple of months ago, I came across this signature scheme of Vadim's, which introduced the notion of rejection sampling. And I suddenly realized that was the answer, except this was the wrong functional. That was the wrong polynomial. The correct polynomial and even rejection sampling would work in something like this also, because think about it, where is most of the information? Well, basically, whenever you do some averaging thing like this, most of the information is coming from the more extreme values. The areas where C or G accidentally match up and magnify effects. And so if I had thought at that time of throwing out signatures where this thing didn't look kind of uniform, then that would have been a big difference, except I didn't think of it. But now using the polynomial that Dean wrote down, a better solution is write H is equal to F times C plus G. Pick C and G exactly the same way. G is a commitment. C is the challenge. F is your private key. Construct this. But now you need to change the parameters a little bit. You need to change this so that G, coefficients of G, satisfy, let's see, the AI, call them AIs, are less than some k and bigger than some minus k. So in other words, let's say that the saying that the infinity norm of G is less than or equal to k. And let's say, let's say that the infinity norm of C is less than or equal to b, using Vadim's notation. Then it turns out to well, and b is much smaller than k. That's, I want infinity norm C, pardon me. Oops. No, this is k prime. No, actually, that was K prime. Yeah, totally different K. Let's see. So choose something like that, much smaller than K. Well, think about it. The intuition that goes on is you take F is consisting of ones, zeros, and negative ones. It's trinary. Roughly a third ones, a third negative ones, a third zeros. C is now thinner, sparser, in such a way that when you multiply F by C, what's the very biggest? The very biggest, the infinity norm of F times C can be is B. What? No, I want the infinity norm to be small. Do I? What? No, I actually want B. Wait, hang on a second. No, wait a second. No, each coefficient. Think about it. Each coefficient of F times C is no bigger than B.
No, but then you add them up.
No.
You have the infinity norm of G over the 1 norm. Any term of F times any term of C has size at most B. But then to get the terms of the product, you have to do the convolutions. You add up.
Hang on a second. No.
Unless you take the L1 norm of one of the vectors. If you take L1 and L infinity, then it's true. But if you take L infinity, you have to add a factor.
Well, let's see. The ith coefficient of F times C is the sum over I1 plus I2 congruent to I mod n of let's say these coefficients A sub I, and suppose these have coefficients C sub I. Okay, A sub I 1 times C sub I 2, right? Okay, so how many of these are going to be picked up? At most B. Oh, okay. Then we have a difference in what we mean by notation. When I say the infinity norm of C is less than B, and when I say the infinity norm of G is less than K, what I mean is that the absolute value of each coefficient is bounded by that.
Yeah, correct. So each term there is at most B, so there are n terms. So you probably want C to be sparse.
Well, no, C is sparse. C is B. Oh, yeah. Yeah. Remember Saturday Night Live when somebody would say, "Never mind." Well, never mind. Yes, blanked out there. So right, C has at most B non-zero coefficients, each of which is 1 or negative 1. All righty. Now, where was I before I was so rudely interrupted? Let's see. Okay, so the ith coefficient of this is, anyway, less than or equal to B, or the absolute value of that is less than or equal to B. Okay, and so the biggest any coefficient of this could get is K plus B. If it happens that the biggest one of this matches up with the biggest one of this. Except that's not likely to happen. That's not likely to happen. And in fact, suppose you decide that you're going to reject H unless the infinity norm of H is less than or equal to k minus b. Now, I think there's probably a better answer than this, but this is a preliminary version of the thing. What I'm doing here is using unbelievably strong overkill rejection sampling. Okay, so using overkill on rejection sampling, if you reject H unless H is less than or equal to k minus b, then it turns out that the coefficients of C, comma H are uniformly distributed inside of 3, let's see, inside of 1, 0, well, inside of, let me just put it this way, the C space times the space of as a space of how shall I say this? Times the signature space. So times the space of stuff with H such that the infinity norm of H is less than or equal to k minus b. Okay. So it turns out, so reject H unless this is the case. It turns out to be extremely easy to show that every single possible that if you do this math, every single possible challenge and polynomial with this property will occur in one-to-one correspondence with every single pair signature of C, comma signature. Very easy. I won't bother to mention why that is now, but very simple. So, and what we're really saying is that let's see. Let's see. Let's see. What we're the way rejection sampling works is something like this. If you have a space, if you have a function which has one probability distribution, and it sits inside of a function with another probability distribution, then if there exists some sort of constant by which you can multiply this distribution by and get it to completely envelop the other distribution, then you can't tell what you're choosing. What I'm trying to say, I have a feeling I'm not going to say this tremendously coherently, but what I'm trying to say boils down to the following fact: that the distribution of signatures looks like of coefficients of signatures, what I should say. The distribution of coefficients of signatures looks like, here's 0, looks like this, where this is the biggest they could be, and it turns out to be uniform for a little interval. And so if this is k, and this is minus k, and this is k minus b, then if you restrict yourself to stuff inside of this interval, then you're utterly safe. It just looks random. If you allow yourself to go out of here, then you're not fitting inside a known distribution yet. You're bounded by an unknown distribution. That distribution is going to depend upon your private key f. And so, you'll be in danger from a transcript attack. If, however, you happen to choose a function, if you could choose, this, by the way, sorry, I should mention, this is now joint work with Joe Silverman and what was my wife's name again? Oh, that's right. Jill Pfeiffer and William White, and another guy who you haven't heard of, but you will hear because he's a very good guy named John Schenk. He's just starting out as a graduate student now at Waterloo, but he is staggering. So just wait and see. Anyway, so these guys are I'm developing this with these guys. Anyway, the point is, if we go to the step, if there is some distribution, if there's some positive distribution, some distribution here, public. If we can find a public distribution that lies under the curve for every single f, then we could push the rejection sampling out to the extent to which we can find something like that. In other words, when it gets down to here, forget it. It's going to be just too confused. But it should be possible to push out the rejection sampling a little bit by doing that. And as it happens with reasonable parameters, for quantum computer level security, you could do this with a level 1 in 5 1 in 5 signatures will pass, or 1 in 8, or with a higher security, 1 in 8 signatures will pass. We're trying to, like I said, to improve that. But anyway, so there you have it, this crazy thing that if I had had the faintest idea, if Vadim's paper had fallen through a time warp and landed in 1995, I would have been a much happier person. But I wasn't. It didn't, and I wasn't. So, but anyways, I believe this about covers everything I want to say. Yes.
Do you think you might ever need to care about the joint distribution of multiple coefficients at once instead of looking at a single coefficient?
I don't see how that could possibly come into play. At the moment, it can't possibly come into play because information theoretically, there's no difference between the two distributions and the one-to-one correspondence. I'm not exactly sure, but I think not. I think what you're saying of worrying about the distribution of multiple coefficients, that boils down to finding a curve that goes below every possible key curve. In other words, you have to choose the most extreme possible accidental correlations between F's and C's. You've got to take into account when doing that. But any such lower bound would do the trick, I think.
This doesn't necessarily say also
No, I'm counting the commitment. It's the space of C comma Z is uniform.
I mean, the space of C comma H comma the commitment to G is certainly.
I'm assuming independence of the G and the C. If that's what you mean. I'm assuming that they are truly random, even though one is actually a function of the other.
No, but I mean, in theory, F can be recovered from C, H, and the commitment to G.
Right.
So, I mean.
But that's the proof. That's part of the proof that these two spaces are equal.
So I think I understand this question, but the commitment to G is not new information. So you can recover the commitment to G from the signature in C. And therefore, it doesn't. And we should just look at the formula.
Other questions? Okay, well, thank you, Vadim.